Good morning and welcome to the second day of the Arctic Futures 2050 conference. I first want to take a quick moment to thank the panelists and moderators from yesterday, as well as the hard-working search organizing committee members who've worked tirelessly to put this incredible conference together. So many things under this great angular roof tent. So let's just give them a quick round of applause. And obviously, as you could tell by the timbre of my voice, I'm super excited to be kicking off the second day with this amazing panel. Their bios, like yesterday's bios, are all in the conference packet. So they sound as good as these people look. It's amazing. What you need to know now are these five fine folks are about to take you on a journey. I'm sorry, Siri, how to fix the Arctic? So like I was saying, these five fine folks are about to take you on a journey, one that starts and finishes on a coast, with each one talking about the consequences of a rapidly changing Arctic through their personal lens. We begin with Maija Lukin with the National Park Service, who describes some of what it is like to live, thrive, and survive in coastal Kotzebue, Alaska. The next three speakers, Matt Druckenmiller and Twila with the National Snow and Ice and Data Center, Ted Schuur with Northern Arizona University, they'll share their perspective on three iconic components of the physical Arctic: sea ice, permafrost, and land ice. They're representing the science action teams within SEARCH that work to synthesize and communicate science. We'll then zoom out from the Arctic and hear from David Behar with San Francisco Public Utilities Commission about how challenges facing the Arctic are already affecting communities outside of the Arctic. So without further ado, Maija, would you mind kicking us off?
Thanks, Gifford. Like Melanie, I too got sick when I arrived in DC, and I promise it's not an allergy to politicians. See if modern technology works here. Uvlalotak, uvanga katak kikikdag rugmirunga lisisoli rogorunga, uvanga kokhluk, Western Arctic National Parklands, Savaktunga. My name is Maija Lukin. I am the superintendent at Western Arctic National Parklands, 3 parks above the Arctic Circle, managed by the National Park Service. I'm from the shores of Sisolik on Cape Krusenstern National Monument, pre-Anilka, around 1977. The enabling legislation of the 3 parks came under the Alaska National Interest Lands Conservation Act, established in 1980, and 2 of the 3 parks legislation specifically calls for the protection of subsistence resources and cultural resources. Part of protecting those resources includes monitoring permafrost, climate change and weather, changes in lakes and lagoons, coastal erosion, and massive changes in the migration of caribou, salmon, whitefish, and other subsistence resources. Today, as in the past, many Alaskans live off the land relying on whitefish, wildlife, and other wild renewable resources. Whitefish is on my mind, sorry, I'm gonna keep saying that because that's literally the time that we're doing it right now. And I keep thinking about it. Indigenous people have used these subsistence resources for food, shelter, clothing, handicrafts, transportation, trade, and other goods for thousands of years. Subsistence and all it entails is critical to sustaining both the physical and spiritual culture of Alaska Native peoples, and it's a really important tradition to non-natives as well. Subsistence users have a unique connection to the land, fostered by tradition and lifelong experience, traditional ecological knowledge, indigenous knowledge, traditional knowledge, It's the system of knowledge gained by experience, observation, and analysis of natural events that's shared among family members. In subsistence, that knowledge is used to find, harvest, process, store, and sustain natural resources necessary for survival of the people who live there. Subsistence is synonymous with our culture, identifying identity and self-determination, and we face challenges daily, from changing weather patterns, diminishing sea ice, coastal erosion, and the uncertainty of migration routes. All northern Alaskans feel the effects today, and this is where Arctic research comes in. The research goals directly affect our subsistence activities, and it's important for scientists to work with hunters and traditional knowledge holders to ensure that projects are completed that benefit both the people directly involved and directly affected, as well as the research agencies themselves. The Arctic Network is a part of the Inventory and Monitoring Network of the National Park Service, and it publishes a weather and climate summary for Arctic parks quarterly. Some highlights last quarter included of the 10 warmest summers on record in Western Arctic National Parklands, 8 have taken place in the last 15 years. Weather anomalies were 8 to 16 degrees warmer than normal. In March, Kotzebue hit 41 degrees above zero, which for many of you isn't that warm. The highest temperature ever recorded in March in Kotzebue, Alaska. Other records were also broken in March, including the lowest sea ice ever recorded over the Bering Sea and the lowest sea ice in Kotzebue Sound. Unfortunately, our weather is changing so rapidly that people are dying. Subsistence food security, and Inupiaq culture is being lost, and thousands of years of data is being washed away with each season's storms. Thick ice is essential for safe travel between our communities. In an area of the world with no connecting roads, winter travel by sled dogs and snow machine happens every single day. You take the metro, we take a snow machine. Our area is about 38,000 square miles, mostly above the Arctic Circle. Within that area are 3 parks, 12 cities, and villages connected by river, ocean, and overland traditional routes used by thousands of years. Both my uncles were lost when they traveled at a normal time in the spring to our camp, fell through thin ice with their snow machines and gear, and we never recovered their bodies. Last year, my cousin went hunting in places he had hunted safely for 30 years, and he never returned. And his snow machine was seen a week later submerged and frozen in place. And this April, a family member of mine went through the ice with her husband and 11-year-old niece. All 3 perished in a place where ice had always been safe to travel. Administratively, as a superintendent, you have to take into consideration things like that. Overland winter travel is important to the Monument Park and Preserve, and the cost to fly in remote Alaska is tremendous. But the uncertainty of the thickness of ice means a higher cost to those of us tasked with managing the land and ensuring the safety of our employees. To ensure that safety, we now have to pay for vendor flights, which we once could have easily safely traveled by snow machine to all 3 parks. And the cost difference to the public is approximately $3,200 per trip, per person. I said before that 13,000 years we've been living in the Arctic for 13,000 years. And an archaeological site, it's scientifically proven. And we've always said 10,000 years or time immemorial, but an archaeological site in Noatak National Preserve was found last summer and dated to approximately 13,000 years ago. So I wanted to put 13,000 years in context in case you can't fathom that, because I really can't fathom that. So 500 years ago, the Great Wall of China was built. 1,000 years ago, Easter Island statues were being built. About 2,000 years ago, the Colosseum in Rome was built. 4,500 years ago, the pyramids of Giza were being built. 5,000 years ago, Stonehenge was built. 11,000 years ago, the Stone Age ended. And about 13,000 years ago was when Beringia land bridge began to disappear. And for 13,000 years, Inuit people were caribou hunting and seal hunting in Northwest Alaska. That's how far my family goes back. Traditional hunting has been taking place in Northwest Alaska for that entire time, and many of the same techniques are used today, orally passed down from one generation to another, and we calculated approximately 650 generations. The tools may evolve with time and technology, but the traditions all stay the same. And in one single generation, we'll lose that information because of the uncertainty of sea ice and the rapid change we have experienced in just my lifetime alone. An easy way to understand what it means to lose 13,000 years of tradition is to look at your fingernail. The length of your new fingernail is about a quarter inch. It's equivalent to 20 years on Earth. Look at your hand and imagine 1,000 years of history. And if you spread your arms wide, the length from fingertip to fingertip represents the amount of time that the ice conditions were safe. Pack ice was abundant, and cultural traditions revolving around that ice were practiced safely. And in just a fingernail's amount of time, all that has changed. In just one generation, the changes experienced by local hunters on the sea ice had threatened the very culture of those passed down traditions of the Inupiaq people. When the ice isn't thick enough for bearded seals to rest, it forces our hunters to travel much further through rough seas to catch our yearly bearded seal. And it's important not only for cultural value, but for the iron-rich meat that Indigenous people get nutrients from. And our choice is eat seal meat or take vitamins. When we don't have the ice cover the traditional knowledge holders are used to, unnecessary risks sometimes can be taken, and unsafe practices are sometimes used just to ensure that we get seals and we get to eat. Unfortunately, that also means that even though my grandparents, my parents, myself, and my children were taught safe hunting techniques on safe ice packs, proper harvesting, and traditional processing, my grandchildren will never, ever experience that. And the cultural resource loss. When we think about the loss of archaeological resources, information that ties our people to the past, the rate of loss is astounding. And keep in mind that my oral history is an oral history. My history is an oral history. It's undocumented until non-natives arrived. So my only tie to those ancestors lies in the archaeological projects that take place. Nearly 5,000 years of prehistory are represented in the 114 well-preserved beach ridges located adjacent to Krusenstern Lagoon on Cape Krusenstern National Monument. Because the ridges accumulated over time, the earliest ridges lie inland, with the most recently formed ridges and bluffs near the shore. This unusual series of beach ridges presents in sequence detailed evidence of an estimated 9,000 years of prehistoric human use of this specific coastline. Some archaeological sites here are older than well-known remains of ancient Egyptian civilizations, and imagine losing those in one storm. Several feet of Indigenous history is literally being washed away with every single year's storm. In an effort to mitigate that, research takes place on the most at-risk areas each summer, but we can't keep up with the uncommon weather patterns or permafrost anomalies that we've seen in the recent years. So as a federal land manager and as an Indigenous person, it's my responsibility to my tribe and my future generations and the future generations of the public who wish to experience this public land subsist off of the indigenous and traditional lands of my own ancestors, and to be proactive about decision-making and mitigating efforts in our parks in areas in such as food security, natural resource management, cultural resource management, climate change, policy change, and safeguarding our rich culture and relationship to the land. The local implications of reduced sea ice and melting permafrost are felt every single day above the Arctic Circle. Our climate crisis is right now. We work with traditional knowledge holders, scientists, researchers, other agencies and projects, and experts towards understanding what our changing weather and our changing environment mean both culturally as well as administratively, and work towards making informed decisions and unique solutions to mitigate those changes for the future. Thank you.
Thank you, Maija. That was very powerful. And up next, we'll have Matt to talk a little more about sea ice.
Thank you, Maija, for that powerful and personal account. I'm grateful for being in this room to be able to listen to that voice. So these next few presentations will address in more detail what changing sea ice, permafrost, and land ice mean for the Arctic and for the entire globe. It is nearly impossible to discuss or imagine the Arctic in 2050 without fairly quickly considering the state and the fate of Arctic sea ice. And when we do, we start at a particular scale, a scale that is likely linked to our personal experience. That may be at the scale of daily life, where one can see the snow machine tracks across the ice, as in some of the photos that Maija just shared. Or it might be at the scale of the entire Earth. If, for example, you are a global climate modeler, like Marika Holland, who we heard from yesterday. We each come with an appreciation for the importance of sea ice, but there are real barriers when we come together with different scales of reference, different scales of experience, knowledge, and priorities, especially when the collective goal is to prepare and adapt for uncertain Arctic futures. Throughout my brief presentation, I will attempt to offer a few thoughts as to how we may look to highlight and frame these divides in the context of rapid sea ice loss. So sea ice is our frozen ocean that thickens throughout the Arctic winter and spring and eventually melts and thins throughout summer. Sea ice coverage expands and contracts throughout the year, and across large portions of the central Arctic, sea ice persists throughout the summer melt period into the next winter. This perennial ice is the thickest of the Arctic ice, and as a result is the more resilient ice that serves as a sort of buffer against variability and rapid change. By and large, Arctic coastal communities, like the ones we just heard about, live almost exclusively within the seasonal ice zone, where they experience sea ice for part of the year and an ice-free ocean for the rest. In Alaska alone, over 80 coastal communities live within this seasonal ice zone across the Beaufort, Chukchi, and Bering Seas, each with their own story to tell about how recent changes in ice conditions have impacted their community. As sea ice retreats from the seasonal ice zone each summer, there's an amazing switch in energy transfer at the surface. And a snow and ice-covered ocean can reflect well over 90% of incoming solar radiation. And in contrast, when sea ice is replaced by darker ocean water, the surface shifts to absorbing up to 94% of incoming energy. When the heat enters the ocean, it is then available for melting or inhibiting the growth of ice later in the year, changing the physical and biological characteristics of the marine environment, and altering the Arctic atmosphere well above the ocean. This makes Arctic sea ice one of the most efficient dials on climate that we have on Earth. Climate studies, like the ones that Marika Holland described yesterday, have shown that the loss of Arctic sea ice accounts for over 17% of observed global warming and over 50% of warming in the Arctic. This is even more significant when we consider that the Arctic is warming at least twice as fast as the rest of the Earth. Yesterday, Marika explained how modeling can experiment. They can remove the Rocky Mountains, for example, to see the response on climate. In a similar way, climate studies can remove sea ice, and more specifically, remove changing sea ice, to investigate how well models can explain the warming that we are experiencing. It is critical, however, that models account for changing sea ice, especially considering how dramatic and rapid the changes have been. Since satellite records began 40 years ago, Arctic sea ice has lost over 40% of its summer area and over 70% of summer sea ice volume, primarily through the loss of that perennial multi-year ice. This loss in Arctic ice is disrupting and restructuring ecosystems. For example, sea ice serves as a platform for bottom-feeding walrus. And as sea ice shrinks and recedes into deeper waters, this platform is functionally disappearing. And as sea ice loss shifts ecosystems, it is also changing coastal communities' access to food sources, or at least raising alarms and key questions for how that access may change. For example, as is the case for bowhead whales and other migratory species, there are many unanswered questions regarding how existing migrations may respond in the coming decades to Arctic sea ice change. Additionally, as the Arctic warms at 2 to 3 times the rate of areas farther south, this differential warming contributes to increasing extreme weather faced at lower latitudes, events which cause billions of dollars in damage and thousands of disrupted lives each year. The smaller the temperature difference between the Arctic and the lower latitudes, the weaker the jet stream. And a weaker jet stream tends to buckle more readily, resulting in a variety of extreme weather events ranging from droughts, heat waves, fire seasons, stormy winters, and flooding. So what does this mean? Again, it reveals that Arctic sea ice is one of the most efficient dials on climate and on the services that we derive from our climate. Yet actions today are turning that dial in only one direction. A study from a few years ago observed a linear relationship between this monthly mean September sea ice area and cumulative global CO2 emissions. These findings allow us to quantify each of our contributions to anthropogenic CO2 emissions as having an impact. In everyday terms, this means that a seat on a round-trip flight from Seattle to Washington, D.C. is responsible for the loss of 15 square feet of summer sea ice, effectively the size of a dining room table. I offer this not as a fun or scary fact for science communication, but rather as an opportunity to frame the disconnect that I highlighted previously, the disconnect between those of us living outside the Arctic and those living within it. It can be framed in the context of climate justice or environmental justice, recognizing that our day-to-day actions that are contributing to the challenges of climate change are being disproportionately felt by indigenous peoples living in the Arctic through the multitude of ways in which sea ice loss impacts their communities. And so as we look to the potential sea ice futures by 2050 or 2100, based on different carbon emission scenarios, we must face the realities of what sea ice loss will mean for global climate, for changing ecosystems, for new economic opportunities, and for the peoples of the Arctic. As we make decisions to pursue aggressive emission reduction strategies, or to essentially do nothing, we will see substantial differences in the amount of summer sea ice that exists at mid-century, or even greater differences by 2100. Collectively, we may choose to look at these types of model projections through a lens of climate justice. Sea ice is a defining characteristic of the Arctic, and as we heard from Maija, one of the best places to exemplify this is in the coastal waters off of Alaska. If we look to the Bering Sea, the last 2 winters have seen record low sea ice loss in winter. This is not all too surprising, given that Arctic sea ice loss across all months, not just September, correlates strongly with increased CO2 and rising global temperatures. However, the swiftness and scale of change observed in the Bering Sea region during these recent winters was a surprise. The region was mostly ice-free during the months of February and March, which hadn't occurred since at least 1850. The shaded gray portion shown here represents the modern satellite era, where we can peer into what sea ice cover in the Bering Sea has looked like on a daily basis. And so if we focus on this period and define the envelope of what is average for the region across these last 40 years, we not only see that the last two winters, shown here by the black and red lines, are well outside of normal for these winter months, but we also see that large variability in ice coverage, we also see large variability in ice coverage, a variability that is experienced very differently depending on the community. Given the vast stretches of open water and the lack of protective shorefest ice, Bering Sea communities experience storm-related erosion, damage to village infrastructure, and lost access to critical ice-based hunting opportunities. Of course, the reason is more complicated than simply the ice is melting. For example, in these years, prolonged periods of sustained south wind helped to keep the ice further northward than usual. Yet it was the ongoing trend of thinning ice that made it more mobile in the first place. However, just as important as why this has been observed is what do we do about it? When a core component of the climate system, of the ecosystem, and of cultural and food systems is rapidly diminished, we must focus on how to respond. In the Bering Sea region, it is very evident that the defining characteristics of winter are being disrupted. Perhaps another way to address the divide that I mentioned between the scales of how we understand sea ice loss is to consider a different model for how we communicate, how we tell the stories of change and of response at the local level. In the past, we have primarily shared stories shaped by science, complemented by the observations and knowledge of indigenous peoples. We might now consider more and more looking at the model of stories shaped by communities on the front lines of change and complemented by the science. For example, the science being done by the climate modeling community. By stories, I'm referring to those that need to reach the decision makers who will put us on course either for no summer sea ice by the end of the century or perhaps on course for a stabilization in the sea ice cover. So finally, it is important to recognize that the observed seasonal loss of ice in the Bering Sea today and in other regions of the Arctic provides a glimpse into what it may mean for all of us to lose the majority of the entire summer Arctic sea ice cover in the coming decades. Sea ice is clearly not only a defining characteristic of the Arctic, but it is a defining characteristic of the entire Earth system. There are opportunities for those well outside the Arctic to learn from those who are experiencing the impacts of rapid environmental change and who know firsthand the range and decisions that must be made to balance competing interests and to respond to climate disruptions. So, thank you.
Thanks, Matt. Up next, Ted and Permafrost.
Thanks, Giff. Well, I'm honored to be a part of this panel and a part of this conference. It's great to hear all the voices thinking about a changing Arctic. I'm going to try to answer 3 questions today for you, and I'm going to talk about permafrost, what it is, why it's changing, and why that matters to us. So this is a view from North Pole, looking at the northern hemisphere, and the area underlain by permafrost is colored here in blue. So permafrost underlies about a quarter of the land surface here, all of Arctic tundra in the northern boreal biome. Permafrost is perennially frozen ground, and if there's one thing that my colleagues will be happy about, is if I can teach you that permafrost thaws, it doesn't melt. And the way to think about this is if you take some hamburger or maybe some moose meat out of the freezer, put it on the counter for dinner, you're waiting for that meat to thaw out, not for it to melt. Now, permafrost ground is the same way. It's made of ice, soil, and bedrock. This is a picture of ice-rich permafrost in Siberia, and the hill is actually eroded, so we're looking below ground here. There's a couple of features that I want to point out on this that will become important during my talk. First of all, we have this surface active layer. It's a few feet thick. In the summertime, it thaws, and then it refreezes in the winter. This is where the ecosystems are active. This is where plants, animals, and people depend on. Below that is the permafrost. It's perennially frozen. These whitish patches here are made up of segregated ice, big blocks of ice in the soil. This view here is about 2 stories high. These patches of ice shown sort of in 2-dimensional, or actually form a 3-dimensional network within the soil here. Interspersed in this ice is permafrost soil with this organic matter. It's the remains of plants, animals, microbes that have all lived in these ecosystems, died, and become incorporated into the permafrost. So, unlike sea ice, unlike snow, unlike ice sheets, we don't have satellite detection of permafrost. So instead, permafrost is monitored through a network of boreholes. These boreholes are a series of pipes that go in the ground tens to hundreds of meters. And we know from this borehole network that permafrost temperatures are increasing globally. So this picture here showing the orange and red colors show increases in permafrost temperature over decades and years. Now, we heard from the last talk, and many of you might know that sea ice in September this year is coming very close to a record low condition. We probably won't beat 2012, but we're coming very close. But how many people in this audience know that permafrost temperatures are at record high conditions? So there's also green dots on this picture, and that's on this scale showing you a slower rate of change. So permafrost temperatures aren't going up as fast as these green boreholes. But this is actually indicating tipping points in the permafrost. Where temperature can't increase is because the ice in permafrost is actually changing to liquid water. And so these are these threshold changes that are undergoing these regions shown in green here. Okay, so what's causing permafrost to change? So we've already heard from this conference that temperatures in the Arctic are warming twice as fast as the global average. We know that we're setting new records all the time. Another consideration with permafrost is disturbances. Primarily, in these permafrost ecosystems, wildfires are a disturbance that affects large land areas. Now, it turns out that fires burn down through the surface soil organic matter, and that acts as insulation for permafrost. So when you burn that away in a wildfire, it actually exposes the permafrost to the warmer atmospheric temperatures. Now, wildfires are part of some of these permafrost ecosystems, but we think that the area that's burning each year, or the severity of these fires, may be increasing. So yes, we've always had fires, but these fires are not the same as they used to be. So this is causing permafrost to change, but why do people care about this? We know that permafrost is defined by its temperature and time, and that's really defined the field of permafrost science for a long time. But from the perspective of people, I'm going to propose that we actually consider 2 other aspects of permafrost. That's the carbon that's frozen within it, and also the ice, those things that I showed you in the picture earlier. Now, this might now be familiar from my talk that these are 3 components of permafrost. Excuse me. I'm going to go back 1 slide here. But if we think about our observation system, we're doing a lot measuring with temperature, but observations of carbon and ice are lagging far behind. Okay, so why does this matter? So this is a picture of degrading ice wedges near Denali Park in Alaska. And what you can see here in this picture of a person for scale is that when the ground ice itself can melt and is removed from the permafrost soil, that the surface of the ground actually subsides. So you get this ground collapse. Now, why this is important is that once this process starts happening, the permafrost can thaw very quickly, and then where the ice is in the ground controls where the ground collapses. So you go through this threshold change that affects everything on the surface, the ecosystems and the people. So why do Arctic residents care about this? Well, these are pictures of infrastructure built on permafrost that's changing. And you can see the effect of the loss of the ground ice and the ground subsidence. From a scientific perspective, what would we like to know? Well, we want to figure out where is this ground ice. We have a hard time seeing it because it's underground. Can we figure out where these tipping points, these thresholds are going to happen and where we might have this abrupt thaw? Can engineering measures actually help us harden this infrastructure and prevent the kind of damage that we see here? So what does science have to say on these topics? Well, this is a map showing permafrost hazard for the permafrost region in these different colors. It turns out if we combine information on permafrost, on ground ice, and on future climate, we can overlay that with infrastructure. And this projection shows us that by 2050, About 33% of all global infrastructure in this northern zone is at risk, and this is under a moderate warming regime. Now, with a map like this, you can calculate these big numbers, but you can also zoom in on different regions. And so this is an inset looking at the Alaska pipeline here in white. And you can see that the pipeline crosses areas of low hazard and high hazard. So it's not all the same in the permafrost region. In a nice regional study by April Melvin, there was a calculation that within Alaska, if we continued on this high emissions scenario, business as usual, there could be up to $5.5 billion in climate-related damages by 2100. But science also has some solutions to this. So one thing we just heard about, reducing emissions globally, climate mitigation, can actually save money. We can reduce this cost by about a quarter through mitigation efforts. Through engineering adaptation, hardening the infrastructure that's in place, we can save about half of this. So there's things that we can do to prevent some of these costs. Okay, so that's a little bit about infrastructure in the permafrost region, and you can imagine that people live there, care a lot about what's happening to permafrost. In full disclosure, I own a cabin in Fairbanks, Alaska. It's built on permafrost. That permafrost is thawing. So every year I have to level my cabin and keep it from tipping over and ending up like those pictures up there. So I really care a lot about this issue. But if you think about people elsewhere, why should global society care about these changes that are happening in the Arctic? And the simple answer to that is that climate change itself might happen faster than we think. So the reason for that, and we've heard, is that what's happening in the Arctic doesn't just stay in the Arctic. And so there's this potential for a feedback loop between changing permafrost and warmer temperatures. So increasing greenhouse gas emissions that are happening globally, warming the Arctic, causing this permafrost thaw, that releases this organic carbon that's stored frozen. Microbes start to break this organic matter down. They release more carbon dioxide, more methane back to the atmosphere, and make this loop go around. So from the science perspective, what we want to know here is, well, how much of the carbon that's stored frozen is going to end up in the atmosphere? How fast is that going to happen? Will it happen over years and decades, centuries even? And will it come out as carbon dioxide and methane? These have two different impacts on the climate system. And finally, plants are growing more and they're taking up carbon dioxide from the atmosphere. So how much will this new plant growth actually offset the releases that are happening from the permafrost carbon? So what does science have to tell us about this? Well, it turns out some estimates show that maybe 5 to 15% of the permafrost carbon pool is vulnerable to release to the atmosphere by 2100 in a warming climate. Now, 10% doesn't sound like a big number, but because there's so much carbon stored frozen, that's equivalent to about 150 billion tons of CO2 in methane into the atmosphere. If you just normalize that to what's already in the atmosphere, that's equal to about 75 ppm CO2. If you go back to Kurt's talk on day one, he was talking about the glacial, interglacial period that just happened over the last thousands and tens and thousands of hundreds of thousands of years. The atmosphere was going between 180 and 280 ppm. It was moving 100 ppm and changing the Earth's climate dramatically. And you can look at what that is for context. So for other context, what's the rate that this carbon is going to be released from the permafrost region? Well, this rate, 150 billion tons over the next century, is equivalent to rates that are coming out of tropical deforestation today. So it's a similar biospheric change as we see with deforestation. It's much less than what's coming out from fossil fuels, of course. But if you think about global emissions treaties, we're trying to reduce these two sources. We're reducing land use change in the tropics. We're trying to reduce fossil fuel use. So any new additional source coming out of the Arctic is just making that much more difficult. Okay, so where are we? Some people think that the permafrost is already gone. Some people think that it's hopeless. But neither of those are true, actually. So this picture shows you some future projections for permafrost. And in blue here, we have a world where we reduce emissions globally. We kind of cap how warm the Earth gets. Red, we follow the current trend and do very little about it. And we can see that we can have an impact on permafrost. So limiting global warming to 2 degrees can save some of this permafrost. For example, if you look at 2050, the year that's the subject of this conference, If we reduced our emissions, we would save an additional 33% of the permafrost that would otherwise be lost by 2050. And that trend just continues as you go out further to the end of the century. A whopping 145% of the permafrost, this additional permafrost, can be saved if, again, we limit global warming. So my take-home message here is that even though we do see that permafrost will decline in the future, we can do something about this. It's going to be important for mitigation and adaptation for these actions to save infrastructure that's in the permafrost region currently, but really, truly, I think global mitigation is our best way to save the permafrost that we have now. Thank you very much.
Thanks, Ted. Twila?
You've now heard about remarkable reductions in sea ice and extensive permafrost thaw across the Arctic, impacting ecosystems, human infrastructure and economies, human lives, and contributing to additional warming. Now we'll turn to a third component of the Arctic cryosphere, land ice, shown here in yellow. Arctic land ice includes glaciers across Russia, Scandinavia, Iceland, Svalbard, Canada, and the United States, as well as the Greenland ice sheet in Greenland. Across the Arctic, and indeed across the globe, we have seen a rapid acceleration in land ice loss over a very short period of time. Over the last several decades, the smaller glaciers around the world, including the Arctic and particularly Alaska, have been the largest land ice contributors to sea level rise. With Arctic land ice outside of Greenland containing enough ice to raise global sea levels an additional 9 inches, ongoing loss of ice across the US, Canada, Russia, and elsewhere will continue to be a major concern through 2050 and beyond. But just as alarming, or perhaps even more so, is the rapid increase in ice loss that has taken place in Greenland. The Greenland ice sheet sits atop the largest island in the world, and at the center of the ice sheet, the ice reaches more than 2 miles thick, equal to about 7 Empire State Buildings stacked on top of each other. The Greenland ice sheet was close to being in balance through the 1970s, 1980s, and early 1990s, gaining about as much mass through snow in winter as it was losing through melt in summer. But early in the 2000s, Greenland ice loss began to increase. And since then, we have seen a rapid acceleration in ice loss. For the last 20 years, Greenland has lost ice every year, and the amount lost has increased. This year, in 2019, ice loss from Greenland has so far been the second largest on record, with this type of record beginning in 1950. While Greenland contributed little to sea level rise before 2000, it is now adding as much water to our oceans as all of the world's smallest glaciers combined. But the reservoir of ice that Greenland contains and that it could contribute to sea level rise in the future is much larger. Greenland contains about 33 times more ice than all of the rest of the Arctic combined. Our scientific knowledge about how much ice Greenland and the Arctic contains and how much of it we are losing comes thanks to advanced technologies like NASA's IceSat and IceSat-2 satellites, which measure changes in the ice surface height, and NASA's GRACE and GRACE follow-on satellites, which measure the total mass of the ice and how it changes. Advances in remote and unmanned measurement technologies are also beginning to facilitate underwater observations so that we can examine where the land ice meets the ocean. What these measurements are telling us is sobering. We're losing unprecedented amounts of ice. Why is this happening? The big picture is that human-caused climate change is increasing air temperature and warming ocean waters. As air temperatures increase, there's more melt on the ice sheet surface, and the melt season becomes longer, beginning earlier in spring and stretching further into fall. There's no longer enough snow falling in winter to offset the large surface melt happening in summer. And once snow is lost from the ice sheet surface, the ice exposed and the lakes that form and streams that form on top of the ice sheet encourage more absorption of energy because they are dark. And they absorb this energy from the sun and create an amplifying cycle of additional melt. And around the edges of the ice sheet, the ice is in contact with the ocean. Ocean waters around Greenland are warming more rapidly below the surface, at about 600 to 1,000 feet depth. All around Greenland, large, fast-moving glaciers are acting as conveyor belts to move ice from the interior of the ice sheet to the ocean. Where these glaciers contact the ocean, warm water can increase the ice melt happening below the ocean surface. This increased melt can drive the glaciers back, causing retreat. In many instances, retreating glaciers speed up, allowing them to bring more ice to the ocean from the interior, and they pull the glacier, causing it to thin and become more susceptible to retreat, creating another amplifying cycle of ice loss. Together, warmer air and warmer oceans are creating a double whammy that removes ice from the ice sheet surface and from its edge. But simply observing this ice loss doesn't tell us about why we should care. For that, we need to look at the impacts of losing ice. And the impacts of losing land ice in the Arctic span from the local to the regional to the global. In Greenland or Alaska or other areas close to ice loss is transforming local ecosystems. As we lose ice, we put more cold, fresh water into the ocean and change the delivery of important nutrients. This changes the ecosystem, including in places where, for example, industrial fishing or subsistence hunting is important. Regionally, as we add this cold, fresh water to the ocean, we're also changing the character of the ocean water and influencing how currents move. The ocean currents don't simply transport water, they transport heat and energy as well. By moving heat and energy, changes in the ocean currents have the power to influence climate in Europe, the US, and other mid and low latitude countries. As we zoom out even further, loss of land ice across the Arctic is increasing sea levels around the globe. The impacts of sea level rise are wide-ranging and serious. As oceans rise, we see coastal erosion threatening houses and eating away at coastal environments. Salt water is able to inundate freshwater resources, and rising oceans can cause problems for stormwater systems, potentially disrupting clean water sources and increasing health concerns. And coastal areas around the world are seeing increased flooding. In some instances, areas are flooding permanently. Other regions are flooding more often, and rising waters are reaching areas that had never had to deal with flooding before. Across the US coast, we're already dealing with sea level rise. As we look to the future, it's certain that we will continue to lose ice across the Arctic. For example, the Barnes ice cap on Baffin Island will disappear within a millennia, even without additional climate warming. But the larger areas of ice, like Greenland, the amount of ice that will be lost in the future and how much seas will rise in the future is closely connected to human actions. In 2050, the difference in sea level rise that will occur if we follow a low emissions, which would require aggressive action, or a high emissions pathway, as we've been following so far, is just beginning to emerge. By 2100, a high emissions pathway that we've been following will create substantially higher sea levels. Unfortunately, research occurring right now on the behavior of ice sheets suggests that it may even be possible for the seas to rise more rapidly, perhaps approaching 6 meters or roughly 6 feet of average global sea level rise by 2100. As we create our global future, it is critical to recognize that the actions we take and the emissions pathway we embark on within just the next decade and the next couple of decades will have impacts that reverberate for hundreds of years. For Greenland, the result of taking a low emissions pathway, which you see here on the far left, remember that would require very aggressive global action, versus taking a high emissions pathway, the one you see here on the right that we're following right now, is the difference between substantial preservation of most of today's ice or total loss of the Greenland ice sheet within the next 1,000 years. We heard from Maija earlier about the long history of culture, oral traditions, and practices that have been developed by indigenous people in Alaska and also across the Arctic. I think many of us might have come here feeling like 1,000 years is a long way into the future, but I hope that you can now appreciate that it's in fact a blink of an eye. So, as we consider the impacts that we're already seeing from Arctic ice loss, we must also remember that the severity of the impacts to come over hundreds of years depends on these next several decades of policy and decision making. It is not too strong to call this a climate emergency, and it falls on our shoulders to look at where we have personal influence with family, friends, organizations, and people making decisions on policies, from policy to business, and to find the ways that we can act and that we can require that they act. Thank you.
Thanks, Twila. And now, David.
Thank you. Good morning, everyone. I'm going to build on Twila's presentation a little bit and everybody else's. And I've been learning a tremendous amount here by leaning on the experience we're having in California. So my place in this tent is California. And I'm going to focus perhaps a little idiosyncratically on the challenges and some of the projections that we're using in California and in the West U.S. in general. And I'm going to focus on sea level rise. And my goal, in part, is to frame the challenge, not really in terms of mitigation policy, which I'm not going to be touching on very much, but more what we need from science and the interaction between climate science and the projections that we use in our planning on a day-to-day basis and the challenges that we face in a place like California. Hopefully I can help answer the question that Marika Holland asked yesterday, which is, what do decision makers need from, I guess I should get my slides going here, from climate science? I'll try to answer that question. So we're in the midst now of understanding our vulnerability, and we're looking at how this vulnerability is going to play out over time and what the challenges are for policymakers in responding to that in real time. It's starting to get fairly real, even as we think along a kind of decadal pattern in terms of the worst impacts of sea level rise. This is a headline from a community called Del Mar on the California coast, Southern California and San Diego area. Managed retreat is already being discussed by a California regulatory body, and Del Mar is being asked, think about managed retreat in your long-term planning. Del Mar has said, no, thank you, we don't want to think about managed retreat. These are fairly large homes along the surface, along the shoreline. And so this is starting to play out already, even as the worst impacts that we're going to see, the kinds of things that Maija was talking about, are still quite a far distance in our future, at least. The adaptation challenge, not to trivialize it in any way, is significantly one for us related to dollars and money and costs. Eventually, we will be taxing our citizens to pay for adaptation. We'll be raising rates, we'll be instituting new fees, we'll be appropriating funding from various legislative bodies and from our tax resources. And that's ultimately one of the questions that we have to ask is, at what time, what is the timing of that expenditure? What is the nature of that expenditure going to be? I don't think we're really going to put a tidal gate across the Golden Gate, and if we did, it would be a steal at $1 billion as the Rotterdam Gate cost in 2019 dollars. But it's the kind of challenge that people are already starting to talk about. At the same time, there's a lot of confusion about how to go about this business of adaptation. This is a new thing that we're all doing. And this is a word cloud from a meeting, or from a session at the 2017 National Adaptation Forum, which is a conference that brings 1,000 adaptation professionals together. 45 of them were in this room and were asked the question, what words describe the current ecosystem of adaptation resilience services? This is a question related to the science, related to uncertainty, related to what kind of translation of the science and uncertainty are you getting? What are best practices in adaptation? How do we go about adapting to this reality and as it plays out? And you can see that there's a lot of confusion and dispersion of this information. Folks are not yet clear on how to do this work. And it's not getting better necessarily. In some ways, it's getting worse. So just to orient toward this slide to start, I'm going to use this a few times. We've got low, median, and high projections for sea level rise. These is 5 authoritative sources over a 5-year period that we've been using in California, starting with the National Research Council's 2012 report on Washington, Oregon, and California, National Climate Assessment, the 5th assessment report of the IPCC. This is the NOAA report that came out the last day of the Obama administration. And this is the Rising Seas in California report that was a commissioned report from a number of scientists by the state. What we're seeing in this trend is virtually no change in the median projections. They're all about at a meter in 2100. We saw some tables that showed that earlier today and yesterday. But a significant change in the upper end projections, nearly doubling between the NRC report of 2012, which was viewed as best available science at the time, to the Rising Seas report, nearly doubling. So from a high end of 5.5 feet to a high end of over 10 feet. This is challenging. This kind of gap, this kind of range is very challenging. It's not something we can't deal with. We have tools that can help us understand what the range of effects on us will be. This is inundation mapping for San Francisco shoreline, focuses on the bay side. The green areas, by the way, are disconnected. They're not going to flood. So 3 feet of sea level rise in San Francisco is not that significant. We're actually very fortunate. We have a decent grade line in a lot of our shoreline. 9 feet of sea level rise, however, is significant. And so this range that you saw in the previous slide is extremely impactful in terms of what the adaptation challenge is for us. And we're preparing for all of these futures. But let's talk about what we need next. So again, we've got, this is actually, this changes a little bit. The blue bars are median, the orange bars are high-end projections, and then we have some extreme projections. These are the projections that we have under the different RCPs. And what's interesting about this, and this is trying to get to the question, what do decision makers need from science, is that the differences across emissions scenario for, just say the high end, are not that significant. 5.7 feet, 6.9 feet. This is 2100, this is 2150, so looking out quite far here, partly to get the contrast clear. But when you're looking at the differences within any given RCP, within any given concentration of greenhouse gases in the atmosphere, the differences, are quite significant. I'll get to that one in a second. So just to pick RCP 4.5 in 2100, sea level rise could be 1.9 feet, it could be 5.9 feet in RCP of 4.5. And so a partial answer to the question, very much a partial answer, what do we need from science is, can we narrow the range of projections? Within an RCP, not the political science of what emission scenarios we might be under in the future, but what can we do to narrow the range within any given emission scenario? Now, the difference in this scenario is that with the extreme sea level rise, the very, very high numbers, obviously we're seeing great sensitivity, and this is largely of land ice, to RCP. So if you've got RCP 2.6, we don't have anything like the kind of catastrophic loss that we're seeing up here. And so obviously greenhouse gas emissions are extremely important in that situation. Not surprisingly, we're seeing a lot of different projections emerge in different jurisdictions. This is some preliminary research that we've done recently in San Francisco on 28 jurisdictions. I obscured the localities because this is still in review, and also because we haven't determined the degree to which vertical land motion is factored into these projections. But what you can see is a significant difference between the projections that are being used at the high end and projections that are being used at the low end by jurisdictions, in some cases the same ones. Here we've got California happens to be the highest, has the highest projections, but here's a jurisdiction in California that's using much lower numbers. Can we get better communication, collaboration between decision makers and between decision makers and scientists so that these kinds of differences are not quite as wide as they are now? Some differences are going to be merited because of a lot of different factors that contribute to sea level rise. But what else can we do? So I want to take one short case study, which is high-end sea level rise. As I mentioned, high-end sea level rise is a projection that's getting much, much higher over time, as opposed to median. And a big driver of that, for us at least, is Antarctica. And this is the Decano and Pollard paper from 2016 that does a number of things related to Antarctic catastrophic melt. Very important science, very interesting and important modeling that Decano and Pollard did. And it got a lot of attention because it really drove the projections of sea level rise in the 2100 period much, much higher than we've had before. It was actually the most cited article on climate change in social media and the news media of 2016. And it resulted in, among other things, some pretty significant increases in the projections at the high end. This is the source of the rising seas in California's projection at 10 feet in 2100, which is almost incomprehensible, is largely the Decano and Pollard paper from 2016. But there's a problem. It was experimental. It was a starting point. It's important and valuable, but it wasn't necessarily the final word. As we saw in 2019 when a new paper by Edwards et al. Came out and came up with a number of other theories that said that perhaps the Decano and Pollard projections for 2100 could be re-examined or should be re-examined. What we get then is another set of headlines that says that the terrifying prediction that we had 3 years ago is not necessarily still applicable, or we don't know yet. And so what we need is more discipline from the science community and the adaptation community working together to interpret new science and to be able to distinguish between cutting edge, peer review research that's extremely important, as the Decano and Pollard paper was, but also between that and actionable information. Science that's ready for application in the real world, where we're raising taxes, where we're raising fees, where we're instituting new costs to actually plan for decision making. I'm going to skip that one and go to a paper that just came out this year. A number of European sea level rise scientists participated in writing. They invited myself and Kate White from the Army Corps of Engineers to participate because the focus is on high-end, go backwards. How do you go backwards? There we go. High-end sea level rise for stakeholder applications. And this paper came up with a framework. It's not the final answer at all, but it's a framework that looks at lines of evidence from strong to weak that should influence decision-making in that way, and looking at plausible worst-case scenarios, which may not be planning projections, but things that you should be thinking about as possibly occurring in the future. This is the kind of discipline that I think can help us to frame the adaptation challenge in an appropriate and timely way, rather than responding to every new study that comes out. It's not that we can't make decisions under uncertainty, as I said. We're prepared to do that. That's part of it. Nobody in my community is asking for a single number. And we understand that these decision points today are different than the decision points that we're going to have tomorrow. We're going to have uncertainty. And we understand that. But can we narrow the range of uncertainty to the extent that planning becomes an easier exercise? This isn't the kind of tragedy that Maija alluded to in her talk. This is the beginning of things. This is Miami a week ago, before any rain, before any precipitation came down. This is nuisance flooding, but it's part of the future that we're all going to face, and it's going to get a lot worse than this. My goal is for us to work together across the adaptation enterprise and then with the science community so that we can respond together. Thank you.
Thanks for those great talks, and this is perhaps the best part, right? Because we've had an opportunity to hear from 5 folks, and now we get to hear from all of you. For those that weren't here yesterday, we do have an app that allows you to ask questions through this device, and then I'll say them. Slido, and that information is up there. If you haven't downloaded the app, feel free to take advantage of some folks that are wandering around, and you could write questions on.
Don't need to download anything. You just do it online.
You could just do it online. Okay, there you go. And there's also the index cards that are going around for those that like the old school paper and pen route. So with that, a number of questions have already come up. And this first question is for you, Maija. You highlighted in a very personal story the very desperate situation for a lot of the people in Alaska. And before this session, you talked about how you actually possess all 3 hats that are represented here in this conference, as a researcher scientist, as a traditional knowledge holder, and as a decision maker. So as a decision maker, how do you think about or start to address the very situation that you presented?
As a decision maker?
Yeah, what are some of the tools in your toolbox that you can put towards the situation?
Climate situation?
Yeah, sure. Okay, yeah, I know. It's a big question. And
it's
Brendan,
kind of a broad question. I think as a superintendent, I'm going to plug the Park Service here. The Alaska region of the National Park Service has several indigenous superintendents, which puts indigenous people from that area in a decision-making seat, or adds another layer of experience when we make decisions. And so I can't speak for any other superintendents or anybody who's come before me, but just speaking as a superintendent for Western Arctic National Parklands, because I have the experience and because I have the history of understanding what safe ice looks like, we just do things like don't take risks on. Yes, it's cost $60 for a snow machine ride from Kotzebue to the Anigak Ranger Station, but there's a patch over here that traditionally we wouldn't cross even with a dog team, so I don't want my staff to cross that. Therefore, we're going to charter an airplane and you guys are going to fly there. And sometimes if you don't have that, indigenous knowledge combined with scientific knowledge, I think if there was a scientist there, they would say, don't cross that ice.
Sure, yeah.
Then some people might think it's not a good use of public funds to take an airplane, but I'd rather stay safe and have my staff completely safe and rather than take any chances, I guess.
No, yeah, I mean, that's definitely something that I think we could all agree on, is that human life is what we're trying to protect,
Right.
And so I think that would be a good use of public funds, or I'd certainly be happy to contribute to that.
Yeah, and I don't know I'm not sure what I don't know what the background of the question is, kind of broad, but, like I said, I'm from 67 degrees north. So, like I said before, the climate crisis is today. We feel it every single day. You don't have to be an Indigenous person to feel it. If you live in Kotzebue or you live in any of the surrounding communities, you feel it every single day. And you don't necessarily have to be related to anybody to, hear about anything. It's such a small, tight-knit place that no matter what, you're going to hear about it. It's going to affect you, or it'll affect your children, or it'll affect your family members.
Right. So maybe in that vein, and because of the limit in characters, there isn't much background to the question, but, does this sort of underscore then in your mind the importance of delivering that story in sort of chorus with other, like either science knowledge and other traditional knowledge, to try and talk to policymakers to act on climate? Or
Political question.
Oh, right, sorry.
I mean, it's really important, I think, to make it make it personal and make people understand. There was the last slide was Miami is flooding, and we've been having flooding for 10 years at least. And so Alaska, rural Alaska especially, doesn't have a lot of representation in the worldwide media unless, a president visits or something like that. But so it's important to make it personal so people can understand the importance today, right now. We're not talking about 2050 in Kotzebue, we're talking about what are we going to do today?
Well, that's very relevant. And I think that's an important message, to make it personal. Another question that has come in is in reference to a comment that you made, David, regarding the range of sea level rise predictions, for example. So like sort of asking the science community to try and narrow that. So to try and turn this into a twofold question, for David initially, do you think you can represent what that range would be for a politician to be able to make that informed choice? Like if a politician were to say, if you can get it to here, this is where I could say, yes, more money, or no, I'll sit until the next election or something like that. And then maybe to the science knowledge and traditional knowledge holders here, like, what are some of the ways that you might imagine being able to refine the products or the communication that you're giving to policymakers? But we'll start with David first.
So the answer to that question is no, not really. There's no desire on my part. I wasn't trying to indicate at all that we need to fit projections into some kind of scale that we can work with. That's not the case. We want those projections to fit into a scale that is as accurate, whatever that means about the future in a non-stationary world, as possible. And I think that the greater discipline for high-end sea level rise is one of the areas that we can focus on. And understanding the sensitivity of land ice, for the most part, Greenland and Antarctica, to melting, continuing to improve what we understand there, because that's the biggest uncertainties as you get out later in the century. In 2050, I didn't show 2050 numbers, but the projections in 2050 are something like 8 to 24 inches, depends on what source you're looking at, under no RCPs at all, because we're not sensitive to emissions between now and 2050 for the most part, although sometimes that's changing. 8 to 24 inches itself is a fairly wide range. So it's not that we can't handle a range, as I said, and it's not that we want a certain kind of range. We just want it to be as narrowed and carefully constructed from an actionable science perspective. This has nothing to do with cutting-edge peer-reviewed science, but from an actionable science perspective as possible, so that we can frame to our decision makers this range as a challenge that we can work with. In the 2012 report for the NRC, it was 3 to 5.5 feet. That's significant, but workable. Now, we're still at 3 feet, and 2100 as a median projection, as a most likely projection, using the models, but we're at this much, much higher number at the higher end. So is that necessary? If it is, we'll have to work with it. If it's not, let's make sure that we're providing translated science for a decision, in the decision context that is as state-of-the-art as we can get.
And maybe just hooking on that term you used of actionable science, does anyone here have any sort of like just initial thoughts related to David's response?
Well, speaking towards the land ice, which is of course a major contributor to sea level rise, this is something that the glaciological community is thinking about a lot, and I work with David in other contexts to try to connect our communities. But the understanding and exploration of how large ice sheets change is a fairly young scientific field with a somewhat small group of scientists working on it. And I would say everyone's doing their best to run at marathon pace because we all can understand deeply how important this is, and that we're trying to understand how rapidly a system can change while it is changing rapidly. And I think one of my biggest concerns is that any decision makers will wait, that they'll put off making decisions in an attempt to get numbers that are better defined. And I think that would really be a shame. And so what we're trying to do is find ways that we can work with decision makers to better represent what we do know while making progress on these outstanding questions that play into those very high projection numbers. So it's an area of need and an area where I think more attention is growing, but that will have to continue.
And maybe I'll just chime in from a related idea, but I liked seeing the paper that you were a part of, Dave, that had yourself and other scientists as co-authors, because it seemed like this definition of actionable science, it's hard for it to come only from the science community. And so part of why I'm here and why many people are here is to build these bridges and think about how do we deal with that. And it seemed like from the title of that paper, you guys were taking these high-end estimates, the ones that cause trouble for decision making, and trying to kind of weed through that and understand how to act in the face of this uncertainty. And you left with that slide and that term of deep uncertainty, which I've become familiar with recently. And the whole idea with that, I believe, is that we must take action when we don't know the future. And so how do we have strategies to do this? And part of it might be doing what you suggested, looking at these high-end numbers, but try to systematically go through them and ask which ones we need to react to sooner and which ones we don't. And I think in the end, a partnership between people trying to make those decisions and scientists and folks living with the impacts is going to be, sort of maximize that.
And I think just to add very quickly, the concept climate services was in the word cloud, but I didn't go into it. It's the place where scientists and decision makers interact. It's the place where translation occurs. I've spent a lot of time executing our own climate services for San Francisco with scientists that I work with. It's an evolving relationship. We can do it better. We can invest in it more. It can occur, very separately from the cutting-edge science work that is extremely important and got us to where we are today. And in addition to that, with boundary spanners and decision makers who appreciate the value of science, and scientists who are interested in working directly with decision makers, which is something like 5% of the total scientific community, or less, and that's fine. We have to evolve that practice, however, in this country more quickly and better than we've done to date, in my view.
I would just argue as a scientist that there's probably more than 5% that are interested, but we don't have the training or the tools or the fora to do that.
Or the incentive structures within academia.
Right, and that was touched upon yesterday, so that's definitely a great callback to some of the discussion yesterday. And I'm going to interject because a lot of this response touches on a couple of questions, so I'm going to try and distill them. But so to your point about having opportunities to have decision makers, scientists, modelers, engineers, in the same room, one half of the question is, how have you seen that work well in the past, being in the same room and actually delving in on a topic that's very specific? And then the other half of the question, which is a little bit of a pullout, and I might have to ask it again, I realize, but is where have you all experienced success in being able to communicate what you thought was the important takeaway, actionable science or actionable knowledge to help inform policy? But maybe starting with this very, like what you touched on, like, are there active venues that allow for this,
So it works extremely well when pursued seriously. The downside is that it's very labor intensive. It takes a lot of time, and the amount of times that the word co-production has come up in the last day plus has been very gratifying for me and will be when I report it to my colleagues, because the concept is entering the lexicon, and that's a good thing. And it basically means a little what Marika said yesterday. What do decision makers need from science? Or what do decision makers need right now? What are the questions that we're asking? And how can we pursue those questions using best available science? That dynamic can be very successful. Did I just cut off?
Perhaps.
I'm back? Okay. That dynamic can be very successful when both parties are interested in pursuing it and sustaining it. I'm actually part of the literature on how-to for co-production of actionable science. Paul Beyer, one of your colleagues, was the lead author on in Conservation Letters. There's lots of literature on this, but and there's lots of literature on the disincentives for this to actually occur. Scientists don't want to be seen as consultants. Decision makers don't really reach out for PhD scientists in our everyday work frequently or at all. But in this brave new world that we're in, it can work, and it is being pursued more and more. The RISA program that NOAA's funded for 20 years has a series of locations, regional integrated sciences and assessments. They all have their own idiosyncratic branding, but there are entities that have worked very closely with decision makers and done some extremely valuable work. The Climate Adaptation Science Centers that the Department of Interior funds are also great examples of that on the ecosystem side. So it can work.
Are there observations on where it has worked in some of the other panelists' experiences? Okay, I'll take that as an answer. That's pretty shocking. No, but I think that points to how there needs to be more mechanisms, and how can we change the reward structures to provide opportunities besides just conferences where we can all be in the same place at the same time. Bringing it back to Maija, there's a couple of questions here, but I think we can start with you and then go on down the panel. Some of the questions are involved with timescales. So how far out should we plan? You had mentioned that these are things that are happening 2019, not 2050. And then particular for you, someone had asked about, have you seen ways where this message of the experience of rural Alaska communicated successfully to, say, the rest of the U.S.? So it's specific to us, but the question is sort of wondering, how can rural Alaska or Arctic Alaska engage in a sustainable manner that reaches down to the rest of the country?
How can rural Alaska engage in a sustainable manner?
Or with the message, I
mean, we tell the message all the time. People just need to listen to it.
Okay. There you go.
I mean,
Yeah.
so, and I think you answered the first question yourself, what's the timeline? The timeline is today. Unfortunately, rural Alaska is very underrepresented in policy and decision makers, and things like that. I'll just leave it at that. But fortunately, we're also a very small, Alaska is a very large state, but we're a very small, we feel like a very small state because we're family. And so, the issues that are happening in Northwest Alaska are also happening in Western Alaska and Southwestern Alaska and Southeastern Alaska and Northern Alaska and Interior Alaska. So the situations that are taking place in Kotzebue and the surrounding communities are taking place everywhere. And if you're not on the coast, it's river erosion, but the loss of cultural resources and the loss of subsistence resources and food security, that's taking place every single day. I think a lot of times it comes down to money. How much money are we spending to mitigate these things? And so in rural Alaska and Kotzebue, just as an example, because that's the example I know, we built a seawall and it was 4,400 linear feet and it was $44 million. So it's $1 million per 100 feet. And so as long as, I think if we put the money side into, policymakers and decision makers' laps, and we say, if we don't mitigate something right now, in 10 years it's going to cost, $60 million just to fix this. And maybe there's a better way if you just listen to the people who have been saying this, there's a better way.
There's a better way, okay. I think, and this touches on previous to yesterday, this idea of storytelling and just continuing to tell stories, and you sort of highlighted how personal stories in particular are really effective. Twila?
Yeah, I wanted to go back to your previous question, and also thinking about Maija bringing up these different costs. Search, putting on this meeting, I think has been trying hard to explore ways that we form and foster successful examples of people getting together, and has worked with, I hope people have looked at the policy briefs that have been, 2 pages, meant to be something that gets in front of a policymaker and it helps explain the science, or bringing people together. And I know from our experience on the land ice action team, we really had to, in part, discover all of the communities that we don't know about. So as we thought, well, instead of trying to find decision makers that might come to the American Geophysical Union meeting, which is where all of our science colleagues get together, we should look where these decision makers, where are they getting together, and we can go find them. And we had a period of challenge just to find the right people in that community who could tell us where they get together. We have a lot of separate spheres, so it can sometimes seem like we're saying a lot of things, but it takes actually a lot of hard work to get into these other spheres that are themselves contained. And one of the challenges in having people brought together is the support for all of the people to be there, and not just support so that people could travel and be in one place for a workshop, but support for the hours and salaries of those people to put in the work before and after they're getting together. And funding sources can be really siloed in the U.S., and that can be a big challenge. And also, as we heard yesterday, and I think even just so far this morning, a lot of these connections require long-term relationships, and show success. There we go. Being able to show success over very short periods of time, a handful of years, which is often what we on the science need to do for grants, is a real challenge in this space. Often success comes over many years. So those are some of the challenges, and I think luckily conversations and connections are being formed so that we can move further along that line.
Thank you for that. We are kind of running out of time. I want to say that obviously I didn't get to all of the questions here, but I think on some level that's a great note to end on, is focusing on the opportunity to build on the relationships, bringing in some of the different stakeholders, with the understanding that there are many stakeholders that could also be at this table Some of the questions pointed out, like, if the stage was bigger, we could have social scientists and engineers and medical doctors and, any number of voices to help bring this forward. But with that, I would like to thank the panelists for their time up here.